One. Okay, so this is a draft science special. So I have Toady, okay, a guy interested in physics, also likes to believe in the truth, let's assume. And he has previously argued, let's just say, pseudoscience types anyway, and sought to preserve some notion of integrity in science, integrity in what people think and how they think, and logic is a good thing and all that kind of crap. Let's apply as much of it. Let's have as much experiment, as much information as possible, analyze it as carefully as possible, and argue about what we're going to assert as being a reality. So anyway, we have a lot of common interests, I think.
Yep, I think that's a bit tricky.
And this is our first meeting, technically, in person. And so he's done a bit of research on the kinetic energy theory, and like me, he's finding a lot of dead ends and a lot of unanswered questions. I explored the history, and the history, in my opinion, is just abysmal. I mean, in terms of the scientific process thrown out the window, and it was all just about who was popular and who could make an assertion and who defined the truth, and evidence be damned. They essentially proved a theory that changed by 50%, right? So they proved mv squared, and then in the 1800s they decided, well, that wasn't really the right answer. Yeah, we proved it, but it wasn't really the right answer, and this one half is really necessary. Now that's our new theory. I mean, it's that bad as science. I mean, it really is. Let's put the brontosaurus head on top of a turtle, and, well, we don't like that. Let's put it on top of the Tyrannosaurus. Let's just move the head anywhere we want to. I mean, it just, whatever's convenient, whatever looks good, in the museum, let's go with that. We won't bother about making sense. We don't know. It doesn't matter. So anyway, that's enough of an intro, I think. So, hi, Toady.
Hi, Gary. Yeah, I think there was, and let's cover the history, right? I put the picture of the lady, I've forgotten the name, Etienne Charlotte or something, in my document, right? 17th, 18th century, these salons were very, very popular, right? For sort of science types, gentlemen, and the intelligentsia, they met, right? And she picked up on Leibniz's ideas, with a pair of compasses, a little portrait, right? Unknown portrait, right? Pair of compasses in her hands. And I'm not talking conspiracy here, but clearly she thought she was a mathematician, and I think square laws were quite keen at the time. They liked the idea of these square laws, right? Because there are a number of things, obviously, in science where we see the square function, right?
Inverse square law, gravity.
Exactly,
I mean, right
exactly.
There.
So she liked that idea. It was mathematical. And then, as far as I can tell from my research, they set up a load of experiments to pretty much validate, this square law that she was, exclaiming about. Faulty experiments, I think. And as you say, they even got that off, right? They realized that it was so astronomically wrong that they then had to halve it. Now, why at that point they didn't just rip it all down? Who's to say? And
well, they were way invested already, because they already decided electrons were starting to move this supersonic speed and had super energy. So they had already built on the rest of their foundations of even Maxwell's equations have this in it, all right? The kinetic energy had already kind of leaked.
Right.
It's already leaked in, and so now you can't get rid of it because
you can't get rid
we
of
have
it.
way too much built on it now. They've built way too big a boat. They're going to tear down the bridge, right? They're just going to do a rich man's solution. Oh, just tear down the bridges that are in my way.
Yeah, I mean, it's terrible, isn't it, right? These open up bigger questions, right? Philosophical questions, which we won't get to today, right? Which really worry me about the foundations of science, because, I watched your video, I saw what you were talking about. It wasn't an area I'd looked at, right? And I thought, look, like I always, I've been involved with maybe some of these, other alternative science types, let's call them that, like flat earthers and that. And normally you can go and prove these things relatively simply. But actually not as simply as you think, right? Which is really quite interesting, right? They're actually, the proofs, let's call it the foundation proofs, are not as simple as you would think, right? Okay, and they never are in science, because science is complex, right? There's a lot of grey stuff that you have to wade through to maybe get to the truths, right? And the truth for me is important, right? Because it's the reality in which we all live. So I think, right, okay, Gary must be wrong. There must be, it must be really simple, and we exchanged some emails, didn't we? And some comments and so forth. I went and looked at Lewin's experiment closely. Call it lecture 16, right, that you talk about. And we may touch on, I'm sure we will touch on it actually. Something didn't quite sit right there, right? It seemed too pat. There were some giveaways. There was this funny bit of clay. you couldn't really see from the camera angle the card and the way the timing device worked and blah blah blah. It just something seemed a little bit off to me, right? So then I go and start doing the calculations, and we'll get into that, I'm sure, because I've looked at those and they're really a little bit odd, right? Okay, if you try and calculate the momentum, if that experiment is correct, you have a device that creates momentum, right? And you can turn momentum into work. And I don't want to use the term free energy, but that is essentially a free energy device. And I don't really believe in those, right? I've had a lot of research actually for a number of years, magnets and Besler's wheel and these other things. Yeah, so I know quite a lot about free energy, or the idea of free energy, 0 point energy, whatever you want to call it, and I'm very suspicious of it, right? Inevitably, right? Because it would, anyway. Yeah.
Well, if it was easy, we'd already have it, because there's only been 1 trillion people trying to make it. So let's just understand, if it was that simple, get real. Of course, I would exploit it if it was that simple. 100 in, 130 out. Okay, I'll just redo that a few million times and I'm rich.
Yeah, which means that if it did exist, right, it's locked up in some lab somewhere. And I'm not a great believer in those kind of UFO type conspiracies, right, where they're powered by these energy devices that only the government knows about. Because again, where are you going to get your scientists to really understand that from? Unless there's a very few, very select scientists, right, outside the normal, and science doesn't work like that, right? My experience of science is, and I've come across science quite a bit in my work. It doesn't really work like that, right? Ideas and collaboration is what science is all about.
Well, I think Joule kind of closed the door to it anyway, just because once they established the connection between energy and work and heat as being the origin of all of it. All of it essentially is movement, and you're really just talking about the tiniest thing moving and calling that your standard, and just saying, so once you know that you have to account for it with a real substance, you can't just make heat. Right. So, I mean, that's a thermodynamic limitation that doesn't poof into existence. So once you know you can't poof it, you have to steal it. You have to get it from something. You already know there's not going to be any perpetual motion. There's not going to be any free anything. It's not going to exist. Well, perpetual motion is sort of a lie, just because we could create a perfect frictionless environment, and you could conceivably have perpetual motion, like throwing a wrench to Mars. It'll keep going to Mars, with one initiation. But perpetual motion on planet Earth is not possible.
Absolutely. And if something like that did exist, it would very quickly become very dangerous. It would be like a weapon, right? Because if you think about the energy, right, equation, what that could create very rapidly. If someone was creating it in their shed,
right? If it was sitting for a million years, it would store a gazillion, bazillion, whatever universes worth of watts of energy. So it'd be the biggest spark.
You'd be in trouble very, very quickly. Right?
the battery would blow up.
Managed to put on it.
Yeah.
Anyway. So, I'm not a great believer. I have looked into it, right, but I'm not a great believer in it. So, his experiment looks very odd. And I watched his other pieces on, elastic collisions and so forth, just to re-educate myself, because I did it, grade school, what do you call it, high school, it's a long time ago, right? So re-familiar, and because of the flat Earth stuff, I'm pretty familiar with momentum and gravity, right? Less familiar, which is also why I by the way, you kept coming up in my feed for probably the last 7 years, but because you're a meme in the flat Earth world, which I inhabited, you're this crazy guy with a hat on shouting gravity or whatever, right? I don't know if you realize you're a meme that's used quite often. I assumed that you were, number one, a free energy nut, number two, a flat earther. I made some assumptions, so apologies, absolutely, Gary. An apology. I should never judge a book by its cover.
Dissidents deserve it. I hate being part of the club, right? It's like I'm a Democrat and I hate being a Democrat because they're idiots and blah, blah, blah. So being a dissident, being anti the establishment is a bad place to be in, because most of the people anti-establishment are anti-established for all the wrong reasons. They're not against the theory that exists, therefore being a Muslim. You know what I mean? It's like the Muslims aren't against Christians, they're just against anybody who's not a Muslim, So all the dissidents are guilty of not being real truth seekers. They're guilty of being shysters and carnival barkers, and they're all running a scheme. They're not doing anything sincere. They don't really believe this crap. Yeah, and clearly after watching some of your videos, I mean, you probably only have to watch one long one or a couple of them,
you realize that isn't, what you're peddling, if you like. I don't think you're peddling anything, but you know what I mean? That is not your argument. And I want to steer away from young slits because, again, that's pretty fascinating, but we won't have time for that today. So we'll stay with the kinetic energy, and we can have other conversations, right? This isn't a one-off deal. If it's useful to you to bounce ideas off someone who's at least can go and research some stuff, and we'll look at what I've come up with in a sec. No spoilers there. Anyway, so I looked at Lewin's experiment, and then I did the calculations. It's really the very, very odd thing about that. And we can start looking for, I don't know whether you can share it, you recorded this, but I don't know whether you can share it, or we can, either look at it together, or I can look at it on a screen, you can look on the screen, or whatever. There's some very odd things that I noticed in it, right? His equation, the kinetic energy equation essentially works out, right, pretty much correctly, which is to be expected because he's doing the experiment, he wants to get that result, yeah. But it's very odd that when you do the momentum calculation, right, it's a reductive, there's two directions, and in theory, if you take one from the other, it equals out, which, like, number one, momentum doesn't, in my mind, work like that. And number two, that shouldn't be the result anyway, right? It's very suspicious that it's so close, almost as if it should be like that. So,
but isn't that their declaration, though, right? That's the convenient part. They just decided to make kinetic energy a scalar and to make momentum a vector. So they just decided that kinetic energy always adds, and momentum can subtract. So direction matters for momentum, but direction doesn't matter for kinetic energy. And that's why they always
Okay. They decided that.
With no cause, no reason, no logic, no reason to make the choice. They just said, we like heads, we'll pick heads.
Okay, so if we just step back a second, we just look at the experiment he did and his calculations, right? And the numbers, I've got them, I sent them in the document I sent today, they're in the one I sent today. If you look at the numbers, right, you start with, in fact, I will bring it up, so I can look at it. Have you actually got it? Could you bring it up so we can look at the same thing?
Yeah, maybe. I I'm using Linux, so I don't like to multitask when I'm recording.
Okay, all right. So I'll just, I'll try and read out what the numbers are, right? Because, they are kind of important. So energy, hang on, and we look at it. So I've done joules. Let's do the momentum, right? Okay. So the starting, so there's one cut comes in. Okay, we'll call it small cut. It hits, as you know, this, I'm just doing for the audience, right? One cut comes in, small cut. It hits the big cut. Big cut goes off, yeah, and small cut goes backwards, all right? So when I say small cut, that means the one that's coming in, and I'll say when it's exiting, okay? So small cut comes in, and its momentum is 195, right, which is its weight of 240 grams times the speed, which is 0.813 meters per second. So it's 195. That's the important number. Okay. So in terms of momentums, right? If we talk about momentums, right? I'll just label it as that. So the momentum in this experiment is an object that's moving along the air track, and it's got 195, about 196 actually, because it's 195.933. So we'll call it 196 momentums. At the end of the experiment, okay, you've got two objects, and they're now going. Obviously, the smaller card is now going this way, and the bigger card is going this way. Okay. Because obviously a smaller object is hitting a bigger object. At the end of the experiment, the smaller card is now going back this way, and it is going this way. Right? I'm not going to call it negative, right? Because we'll get into the whole debate about whether it's a scalar or a vector, but it's going this way, and it's got 64 momentums. All right. The big card now going this way, okay, seems to have picked up more energy than there is in the experiment, and has now got 258 momentums. Now, if you took the 64 away from the 258, you conveniently get very, very close to the 195, okay? Which is what makes me, it really stinks, right, that those numbers are so close. Because then when you do the calculation, of course, for kinetic energy, it works. He shows it on the board in lecture 16, and that's all good.
But I think it also needs to be stated that this is for a cart that's twice as massive.
Yes.
Okay, so,
Sorry.
they do the experiment, but they don't tell you what the mass of the carts are, because if you change the masses, then you can get this result. It'll look like 2/3 because, of the velocity, because the mass is much heavier. So if you make the first cart 2/3 of the mass of the second cart, right, so it's much heavier than half. So if you make the small cart much heavier than half, then the velocity numbers can actually make sense. You can actually have it look like 2/3 the velocity was exchanged because you have the momentum is in the mass, it's not in the velocity. And so then you can actually make this make sense. But you can only make it.
Yep. So later we'll have a look hopefully at the things that I sent through. You can put it up.
Did you see the second experiment in that video? I've shown it in my videos.
The one where he accidentally bounces.
Exactly, because in that experiment we see the exact what Descartes would have predicted. That is, the little cart continues in the same direction at 1/3 the velocity, and the 2-mass cart only has less than half the velocity. So when he's doing the same, what's supposed to be a 1-mass and a 2-mass cart. In the one experiment, it does exactly what Descartes would have predicted. And in the other experiment, right, the first experiment where he's trying to prove the formula, it does this special thing. So they're exactly the same experiment, essentially. It's a 1-mass hitting a 2-mass. And because they didn't stick, it was an elastic instead of an inelastic experiment. Right? So exactly the same experiment. Technically, they're exactly the same experiment, and the outcomes are completely different.
So when you look at what he did in that video with the timers, if you actually slow it down and have a look at the middle timer, right? So there's 3 timers, right? Okay, one time is the one coming in, one coming out, and the bigger
one
cart.
Going back.
Look at that middle timer. The numbers bounce around in it all over the place. Looking at the actual times that are given, right? They look very, very odd. So it goes to like 85, then it goes back to 35, then it goes to 98, then it goes to 130, then 159, then 186. Yeah, and it's very hard. The other timers, you can see very, very clearly that they're going up, counting sequentially. So I don't know whether they were using maybe a shorter card, because on the back of those, as it goes through the diode and triggers it, the way that works is, if you had a hole in it or something, it would like reset it basically. So, it's supposed to have a 10 centimeter, I think they said, strip of card in the back that goes through those diodes. It's, you can't see the back, so you can't actually see how long this card is. And then what I did is I tried to measure the frames as well, as I'm sure probably you try to do, which is quite hard, and it looks about half the speed. So certainly not the speed that is shown on there. So anyway, what then resulted? So from that, what it is, I went to look elsewhere. And I found a video, which I'm sure you did, where a lady is showing you how to set the air track up, right?
Exactly. Arbor Scientific is the company that made the video.
No, so it's not that one.
Oh,
this is a lady called, and I've given you the link in the second PDF.
Okay.
She's called Brenda Tobin or something.
Oh, okay.
And she doesn't work for the company. She's obviously like a science
teacher.
Educator.
Okay, yeah, so I've seen it probably. She's a teacher. Okay, she doesn't give the masses. That's the problem with her video.
No, we'll get to that, Gary.
Okay.
So what she does is she sets it up and she levels it. So really the video is about leveling it. And then she just happens to show you, right, luckily, exactly the same collision, right, with, she uses 2 carts. And you're right, she doesn't give the masses. She uses a yellow cart and I think a gold cart and a red cart, okay? I know where she's bought it from. She's bought it from Fisher Scientific. And then she bounces the 2 off each other. And she shows you, luckily, the numbers again recorded, right? And like she's not doing this to prove anything. She's just like showing you how the counts bounce, right? So I'm very confident that what she is showing is genuine as far as it goes, right? She's not trying to prove anything. It's not an experiment. She's just showing you carts bouncing. If you then go to Fisher Scientific and you look up the cart weights, you can get the cart weights, yeah? And I give them in my document and a picture from their thing, so it's very, very clear. It's like 100 grams and 300 grams. And of course, lo and behold, if you work it out, the momentum is virtually perfect, right? If you work those figures out, momentum matches perfectly. Of course, the kinetic energy doesn't match at all. I mean, it's out by a massive factor, right? Which makes me think that if there was something going on in Lewin's experiment, they must have messed with it quite a lot, Gary, right? Because, the joules are out by, like in her experiment, right? Like her input is something like 3.2 joules. Right, because remember, she's got a little one going very fast, right? Yeah, she's got like 3.2 joules going in and like 0.9 joules at the end, right? I mean, where did all that energy go? It certainly wasn't conserved. So,
I think you really can fake the experiment just by making the light car heavy. So if you make the light car much heavier than half, all right, then because then you start with that much higher joule number. And so when you're when you're giving the velocity to the double mass cart, you're not giving away as much momentum because you already have your mass and momentum. You know what I mean? You're not giving that, you're not doubling that factor, right? You're not saying I'm going to make it twice as much because the cart is twice as heavy. Now you're only multiplying by, 1.2 or 1.3. You get it? So instead of multiplying by 2, the velocity, you're only multiplying the velocity by 1.2 in terms of the change in the mass, right? So instead of 2, because you have double the mass, you're not doing that double the mass thing. So you can sort of understand that there's a lot,
Right.
there's a
So
lot
you make
less
it a lot
percentage
closer.
of the total momentum of the first cart, a lot less of it's going into that second cart. When the first cart is heavier, it's less of the
Yeah.
momentum is going in, and that's why you have the extra to go the opposite direction if you put a spring on it. You put it, all the spring does, the springs versus no springs, all the springs does is change the direction. It keeps going in the same
How does the
direction.
spring change the direction? Surely, that if it just bounces off, right?
But that's what I'm saying is that in a true kinetic experiment, it won't just bounce off. It'll keep going with the cart. It'll keep going in the same direction. The spring allows for that energy to go in and then push back out both of them. So it gives the heavy cart a little boost and it gives the light cart a boost in the opposite direction.
Oh, I see what you mean. Because of course it's going like this.
Right,
and
it
then it's
compresses
going
and then it redistributes the energy evenly instead of redistributing based on mass, right? The spring is an honest player and says, I'm going to give 50-50 this way and 50 this way.
So why did he have 1/3 and 2/3? I never understood that. Why he was using multiplying by 1/3 and 2/3, right? Rather than multiplying everything up. Why was he apportioning it by 1/3 and 2/3 just based on the mass?
Well, that's the consequence of the combining the two to make the equation. So the equation dictates the 1/3 and 2/3.
What? Because he solves it and he's got like 2 minus 1 or whatever when he did it on the other side.
Right. So it's just he's just validating what the math creates. And so I think there's a whole linear. You can put the whole thing on a chart and you can figure out as you increase the differential in the masses, you'll have a line that'll be drawn. And 2/3 just happens to be what happens when you're at 1/2. So as you make it heavier and heavier, that number changes, and but it's a line that you could draw, and you could predict it. You could say, okay, what if the mass was only 10 grams heavier? What if it's 20 grams heavier? What if it's 30 grams heavier? And it'll be all on that line. And it just happens that 1/2 bisects 2/3.
Right, it means they must have done a lot of messing around. They must have known what they were doing. Right, because her experiment, right, was just like offhand, like it wasn't even really an experiment, yeah, and it absolutely works out as it should do. So then that makes me think, why, when you look at things like braking distances, where they're not trying to prove really well, number one, right, they use the the formula, right, and they get this crazy result of 4 times, double the speed, 4 times the stopping distance, right, which is just clearly wrong, because you get frictional losses and all sorts of things, and then these scientists looked into it and they sort of modified it a bit and made it a bit smaller, right, a bit more believable. Okay, they took the stopping distances down in the second lot, right, I found, because
well, I thought kind of a substantial difference, really. It's almost like they were almost saying it's barely a little bit different. It was almost exactly what you expect in terms of half. Like if you were going twice the speed, it was almost just a little bit more than half the distance. A little more than twice the distance.
A little bit more than twice the distance.
Right, which was way off from the 4, right? That's way off from 4 times.
Yeah, and the reason they were doing that, understandably, is in law, if you're taking people to court based on the roads and the skid. In the UK we do it, right? In the UK, if you have a road traffic accident and you have these skid marks, right? People measure that and then they try and work out what speed you were going, right? And if you're working that on a 4 times table, you're prosecuting people who maybe weren't even speeding potentially, right?
Well, that's the scary part of it, is that it's so bad that we could actually be fooled by something like that, where they have statistics and they're not really based on actual experiments, and everybody has this completely false notion. Now, I would still say that you can have the expectation that fast things have less friction. So obviously, fast things will go further because they're incurring less friction per foot. It's just a fact. The faster you go, the less you're touching the ground. So it's
Right.
just like the energy of a dragster, right? Dragster spins its wheels. Well, obviously, if I made the dragster heavy enough, the wheels won't spin, and I'll get
No.
all the motion out of my engine. My engine will be 100% efficient. My
Yeah.
engine's 100% inefficient, if I let the wheels spin. So obviously, fast things are less friction, so you're losing less of your energy technically.
Yeah, that's a very good point, because I was wondering why it isn't even closer to where we'd expect it to be. But of course, you're right. You've still got that downward gravity, right? It isn't an air track, is it, that they're on at all, right? It's a road, right? And they're going, yeah, okay, I hadn't.
And it's four times more burdensome to the heavy object. Just as you need to go 4 times higher in gravity to get get twice the velocity. Well, to get the same thing was with friction and gravity. Gravity is imposing 4 times more friction on the heavy object than it is on the light object. So the light object's getting a much freer ride than the heavier object in terms of losing its energy to friction. Friction is sticking to it, where it's not sticking to the light object. Light object, very little stickiness. Heavy object, a lot of stickiness. It loses its energy very quickly. The light object loses its energy very slowly.
Yeah, I hadn't thought about that, because I was thinking it's sort of, as I said to you, because they basically, just so the audience know, there was an investigation into it, right, where they actually looked, they got, some, Virginia State, I think it was, they actually got them to go back and look at it to see, if these braking distances were accurate, right, and they found out essentially they weren't accurate.
Well, it's just so easy to, you can just recognize so many circumstances where this happens, like sinking in mud, you know what I mean? Or all these things where you can't understand friction as being fair cop. Friction isn't a fair cop. It'll treat it'll treat them very unevenly in how it pulls the energy out of the object. It pulls it out really unevenly.
Yeah, I hadn't thought about that. You're right. So, coming full circle, So number one, I'm pretty convinced that the history of it doesn't really stack up. I never understood the squaring, but I never really thought about it before. I've now thought about it, and why square it? Like, why? Why should it be squared?
And how do you even understand a squared velocity, right? You can't really understand it geometrically. There's no geometry to a squared velocity.
Yeah, that's what I mean. I'm really struggling with why would you square it, right? What is the purpose for that? Yeah, because you kind of at school, you accept these things, you're told them. You don't really question them, and you do some experiments, whatever, we didn't do that experiment really, right? We were probably looking at calculations, I seem to remember, between, potential energy and kinetic energy, right?
Well, that's the tricky word, right? Because as soon as you say the words potential and kinetic, you get a real understanding of those two concepts. So kinetic energy becomes very legitimate in that conversation. In that context, it makes perfect sense. Kinetic energy versus potential. But, that's why they fool you, right? Because they've given it a label that has prestige in another environment, right? It's a general in the other army, but it doesn't mean it fits in this one. It gives it any credibility in terms of the comparison between momentum and kinetic energy. There is where it all falls apart, because momentum has the integrity. Momentum is conserved, okay? Momentum is the real deal. I mean, Professor Lewin has a little clip where he says these exact words like, you can finagle kinetic energy, but nature can't finagle momentum.
Yeah, well.
And yet he did the free momentum experiment, right? So in spite of saying those words, he does a free momentum experiment,
So, I'm on board. It looks odd. The experiment looks odd. I found another experiment. It gives a completely different result. It validates the momentum one. I've gone and looked at these car braking things, right? Again, they don't fit, right? But your point, they're modified more, so they're not really the best case. Yep. So then my thought goes to, what else can we look at? Because this, it should be relatively simple, really, to put this one to bed, right? Yeah. Unfortunately, I don't own an air track. I don't think you own an air track, because otherwise you put an experiment like that on. And why haven't any of these big science guys picked it up? Have you spoken to the Steve Moulds and the EV
I've emailed
blogs
all of them. I've offered actually real money. I mean, I've offered $3,000 to one of these, more prestigious talking heads to even play a 15-minute video of mine. Just play the video. You don't even have to respond to it. Just play it on your channel and prove you've acknowledged my argument, okay? Because it's a valid argument, needs to be heard, and that's the part that's annoying. They just won't give you the time of day. But I have emailed the colleges. I've emailed the people who, do experiments online. The professors on their off hours do these experiments, and I've tried to persuade them. Well, could you actually do the experiment and tell me the mass of the cards? Because they actually have a 1,000 frames per second video of the air track experiment. Beautiful. I mean, it just takes 3 minutes for the two cards to hit each other,
wow.
right?
Yeah.
It's so beautiful. And they don't tell you the weight of the cards. So you can't do anything with it. It's absolutely useless as a piece of... You can't do the math. You can't do anything with it. You're saying, why would they publish this without the masses? Because you can do nothing mathematically. You know what I mean? It's totally useless as a piece of educational material because without the masses, it means nothing. Yeah.
Yeah. That does seem odd, doesn't it? It seems odd that no one's put one, somewhere online where, you have a tape measure. As you say, you have a slow camera. I mean,
like I said, they have it. It's
it?
beautiful, but it doesn't mean anything. What the mass is, it doesn't mean anything because if the small card is 3/4 of the mass, then you should expect the results that Professor Lewin got. But it's only because
presumably they probably don't want to get involved in a controversy, do they? Right?
Well, yeah, exactly. They know that it's dicey, so I think that's all. I think that's what it's evidence of. I mean, also in Professor Lewin's video, right, with the air track, you can see the tape measure is upside down. Why would you turn a tape measure upside down? I mean, in your wildest fantasies, can you come up with some reason why you would turn a tape measure upside down? It looks better. It's cooler. It's a yellow line with no.
No, these are physicists, right?
Exactly. They should love tape measures, right? I mean, they should
right?
They should want tape measures everywhere. Okay, they should never be turning a tape measure upside down.
It does seem very odd. So, how long had you been, talking? Because did you put in? Was that an AMA with Mr. Lewin, Professor Lewin?
Did I put in what?
Was that like an Ask Me Anything that he did? Like, because you put in a question to him, did you?
No, I never got to. He's said things about voltage. There's two voltages in one place or whatever, and he barely responded to a comment I made on that. But after that, I was, I think, blocked. But he reviews comments, but he won't. I actually emailed him 10 years ago and told him, look, I have a better theory than all this crap, and I'd like you to. If you would, I would just like your opinion, blah, blah, blah. And he said, well, I can't look at it because, see, I'm working on all kinds of ideas myself. And so, so he gave me the sort of a patent argument, like I can't listen to it because I might want to patent.
Because it might,
So it was like, okay, well, I'm stuck, But I have made videos where I actually have played a whole 50 of his 1 hour long videos and I critiqued it as I played it. So I've used Professor Lewin throughout the 10-year history. I've used him in a lot of places. So that's why I was aware of this experiment, because I had seen these experiments. And when I thought about kinetic, I finally went and looked at his and I said, oh, here it is.
Yeah, here it is. He's done it, right? It does. It's got a very nasty taste to it, hasn't it? Because it just makes you think, what else,
Well, this is, I started on gravity, okay? So I initiated this whole channel with the subject of gravity, right? And then it went to the two-slit experiment and, the wave versus particle theories, let's just say. And then you get into relativity. And this I fell on. I mean, this wasn't even one that was on my view scope, for the first 7 years of this channel. And it was just that all of a sudden it came up in a conversation and somebody said, 1/2 mv squared. And I said, I've always hated that. And I said, what is that exactly? Where did they get that from? And then when I went to look, and they kept saying F equals ma was Newton, and I believed it. I didn't have any reason to doubt that that's what Newton said, but Newton didn't say that. That was another.
Did he not?
No, it's not a Newton. That's not what Newton's formula. Newton's formula is
really?
that energy, if you want to call it that, right, equals the change in your momentum over a change in time, which really just means that if you want it in seconds, you can have it in seconds. If you want it in minutes, you can have it in minutes, right? So the force equals the change in your momentum over a change in time. So if I make the time the total time of the experiment, right, then I change that t into a 1, and then all I have is force equals your change in momentum. So he's basically saying force equals momentum. If you have zero momentum to start, I give
Right.
you momentum, force equals momentum. So there's no mv squared, there's no F equals ma. So the whole problem with F equals ma is you're saying, why would Newton say A anyway? What is
Yeah.
A? A is a rate. How can I
Yeah. A
multiply
rate of
times a
change.
rate and get an answer? I need to know how long the rate happened. So unless you have F equals A M A T, unless you put the time that the rate's being
Yeah.
imposed, you're not going to get an answer anyway.
Yeah, why would he have said F equals? You're right. Doesn't make sense, does it? He wouldn't have said F equals ma. There's no way he would have said that, would he?
It just doesn't fit with any of
Yeah,
his.
it just doesn't
doesn't
work,
fit
does
with
it?
any kind of material momentum mechanics, and that's what he believed in, right? And so you find out that Newton actually opposed Leibniz's theory. And it was all caught up in that. The problem is that Leibniz was accused of stealing Newton's calculus, and so
Right.
this controversy got lost in that controversy. So it was only Newton's surrogates who argued against Leibniz. But the fact is that nobody believed Leibniz, right? Leibniz died an absolute nobody. Nobody went to the funeral.
Oh, really?
Yes, yeah, he was completely.
So what happened then to?
He was completely disgraced, and his body was essentially dug up by the French woman, and she reanimated him, But he had lost the war completely. I mean, Newton was buried as a god, and Leibniz was a nobody, and they died, within 5 or 6 years of each other.
Yeah, very close. Yeah. So she resurrected Leibniz. Well, that's very
Yeah,
interesting.
that's all it is. She was a big fan of Newton's, but she had read Leibniz and liked Leibniz's philosophy. So his philosophy
right,
was
the
of
religious.
solitons and monads and all this religious crap. She liked that crap, and she figured the mv squared was part of that wooey, fun, free will kind of fun physics.
You see, right. It's amazing because when you come back to grade school, the reason that kinetic energy never really, the formula never, kinetic energy, as you say, as a concept, I think is fine, right? Yeah. Potential energy, kinetic energy, you got what they call roller coasters and things. Concept is fine. I think the thing that didn't sit well with me was we'd done a lot of experiments with momentum, right? We'd done cars that were going along and measuring ticker tapes and all this kind of stuff. Right, this shows how long ago I was at school, right? Ticker tapes, yeah. You didn't have cameras and timers and things. So, we were doing these calculations. And so, P equals MV was fine, right? Okay, yeah. So the calculation for momentum I was pretty familiar with. And then suddenly you got this other crazy thing and they're squaring it. And that's why it never, not that I ever really questioned it, right? I'm not saying I ever questioned it. But you know what I mean? That's why it probably never sat well with me.
Well, I'm just saying it never. Yeah, I always saw it as an outside. I always saw it as an abstract formula that rocket fuel scientists used or something. But you never would use it in real life. Like you'd never measure the energy of a snowball, with mv squared. Because you knew it was about weight, right? You knew that the faster it's going, the heavier it is. That's how I always understood mass and velocity. It's just weight, right? If I jump off of a table, I'm just adding weight, to my matter by giving it velocity.
But the crazy thing is, right, I also had quite a lot to do with guns and shooting, right?
Exactly, yeah.
Right. And again, right, they're trying to do foot-pounds there, right? Okay. And, ballistic pendulums, right? You shoot it in and you can get... I really question why no one has come across this, right, in standard, everyday engineering. Yeah, because according to this, right, if I get two hammers, right, I just have to whack the hammer a bit harder and I get a lot more energy out of the hammer, right? So why have a sledgehammer at all?
Exactly. I've made the argument.
Yeah.
Why there's wrecking balls using wrecking balls? Why don't they just go back to bullets or something lighter and it's infinite. It goes infinite in a way, right? So you're arguing, what I really should do is throw dust at everything. Right, just because I'll have an infinite amount of power. If I can find an infinitely small thing, I can have infinite amounts of energy because I can move it with a gigantic thing, moving slowly, that has a tiny amount of energy. So I can put a tiny amount of energy in, and as long as I just keep getting, it's like the lever argument, right? You keep making this lever argument, but you keep reducing the size of the object, put it further and further out on the lever, and theoretically, if you could make a perfect lever, I can put a bullet there. I can make it go 1,000 miles an hour.
Hey,
merely by going far enough out on the lever.
You have to explain it slowly. Go slowly.
Well, I'm just saying you have a fulcrum on a lever, right? And the fact is I can balance a 2-mass weight here and have a 1-mass weight way over here. Okay, twice the distance, and they'll balance. And I could basically go all the way to the gun and the bullet, by just putting the bullet further, because the bullet is 1,000 times fewer atoms. So I go 1,000 times further down the lever, 1,000 units of distance, and then I can have the gun and the bullet.
Right.
You're always going to get there. And so that argument to me is so compelling because, I just can't make that lever, right? I can't make a lever light enough and strong enough to go 1,000 units of distance away to make it go fast enough. But in theory, that's exactly what I'm doing. A little tiny distance here, a big giant distance here on the other side of the lever, big giant velocity.
But how come when you've got the gun and the bullet, right, there isn't more? They're going to say that gun hasn't got the same energy, right?
Right, because I'm not going to deliver it in the same amount of time. And that's the difference, right? The bullet delivers all the energy at once because it gives, as soon as it hits something, it gives it 1,000 miles an hour. So it's like the Madame Chartelet experiment. She dropped things into sand. And then she figured because the high velocity thing, the sand goes further. Right? The little pieces go further, but it's much fewer pieces, right? The slower thing, they don't go far, but you hit a lot more of them.
There's a lot of them.
You move a lot more sand. So if you take the total distance that a piece of sand actually moved and add up all the distances, it's the same. The 10-ton train going 5 miles an hour, same as the 5-ton train going 10 miles an hour. Same energy, same capacity to move matter in the universe. And the bullet, one atom going 1,000 miles an hour is the same as 1,000 atoms going 1 mile an hour. Same amount of weight, same pressure, same ability to push things in the universe. Same money. I used the comparison of money, right? $1,000 bill is the same amount of money as $1,000 bills. Same money.
Yeah. I hadn't thought about the time factor. Because, of course,
Well, the first pin, say an 8-pound bowling ball is going twice as fast, right? The first pin it hits, it gives 40% of its energy away to the first pin because it goes away very fast. It goes away as fast as the ball was going. 16-pound ball is going half as fast. It can only give away eighth of its energy in the first pin. That's the huge difference. So the fast thing distributes its energy much faster than the slow thing. Than the heavy thing. The heavy thing has to take time to get rid of its energy.
Yeah, you can't do it so fast, can it?
Because it can only give each object it hits the velocity it has. It can't give it twice the velocity. It can't give it 3 times the velocity. It can only give it the velocity it has.
So why do they come up with this, notice this phenomenon when you're done golf clubs, right? Golf clubs need energy, right, to hit whatever golf balls, I presume, right?
It's a lever.
Certain distances.
It's a lever.
Yeah, right, exactly. Yeah, So again, I just, there must be somebody who studied it and just gone, this is a load of rubbish, we'll just use momentum or something. There must be...
Well, I think that's all the practical part, right? If you're designing a bridge, you care about big, heavy masses moving. You care about what's moving, the asphalt's moving, and so they just use momentum. And NASA already concedes it uses momentum. It concedes it uses Newtonian physics to navigate space, okay? So,
they concede it.
Okay, so they're basically implying that, yes, we're momentum physicists. We're not, the KE formula was not in the lunar module, okay? It didn't bother with that nonsense. It just cared about how much gas it was ejecting in what direction.
Yeah, exactly. Got to fight against gravity somehow,
Because it's just a fact that the two formulas, if you use one formula or use the other, the fact is you will crash on the moon. You know what I mean? They won't both let you land on the moon. If you use one formula, you will have your thrust.
Well, that's what I mean. Or you'll end up floating.
You'll have your thrust on longer than you will if you use the other formula. So you really do have to pick one. You can't say they're both right. Okay? One of them's getting right answers. One of them gets wrong answers. I'm saying the overwhelming evidence is momentum has gotten a lot more right answers. You have to go with it.
So why? Lewin covers it because he's covering everything in his lecture series. I'm just wondering why he's laboring the point so much, I suppose.
I just think that they have to give it some sort of underpinning because of the fact that all the quantum mechanics is full of it. You know what I mean? They need it to create all the energy that makes accelerator, all the accelerator data is built into it. A linear accelerator completely dependent on mv squared to define the energy of the particles they're shooting. It's all completely woven right into their understanding of atomic energy.
So why are they not noticing problems there then?
Well, because there's no way to prove. You know what I'm saying? They're telling you what the energy. It's like as I can walk up to you with a gallon of gasoline. I could say there's 768,000 joules of energy in this. What? I'm going to doubt you? You say so. Okay. Did we ever pour it into a joule machine? You know what I mean? Did we ever do the test? Where we got 100% of its heat out of it and saw how much heat it had? Nobody did the test. Nobody's tied the 10-ton train to the little joule energy tester. No one's tied the 10-ton train and then tied the 5-ton train and done the experiment. Nobody's done the experiment.
Still,
I'm just saying, as soon as they do it, okay, then this is all done. We're done, right? We've resolved it. We'll do the tug of war between the 10-ton train, the 5-ton train. Let's just get it over with and we win. Because I'm just saying, I'm so confident. There's no way the 5-ton train wins.
No, I mean, you're right. It's just going to sit there.
They're just going to go like this and stop, okay, and fall apart or whatever they're going to do. But one of them is not going to decisively win.
One is not going to drag one this way.
It just ain't going to happen.
I'm just surprised that, I don't know, I need to go and, read back about some particle physics, right? Because I'm sure they've done tests with electrons quite in the early days, right? Sort of when Cook and
I understand. Once you open that's another thing. You start scratching it, it's all plate. Okay, there's no solid gold here. Okay, because I've done it. I went through and researched some of this stuff, and you're watching the linear accelerator, and they say how it's all about the voltage, and that decides the speed of the electrons. Well, guess what? The speed starts at 98% of the speed of light. And it goes to 99% of the speed of light. There's no linear change. They can't make a photon go 50. They can't make an electron go 50 miles an hour. They can't make an electron go 170 miles an hour. You know what I mean? They can either make it go 98% of the speed of light or 99% of the speed of light.
Right.
Okay, but they can't make it go any other speed.
Yeah, so it's right up here. Yeah. Okay. All right, I need to go and think about that. Right. Well, it's been very nice.
Yeah, I really appreciate it, and so I'll look forward to the next conversation. And I'll. Is it okay to post your PDFs, or do you want me to wait
absolutely.
On that?
Yeah.
Okay,
I'll just check that there's nothing. Obviously have a look through them, but yeah, absolutely post them so that people know what we're chatting about.
Yeah, just to the context of the conversation, and
because there's pictures in there as well when you see them. Because remember, there's two. There's another one that I sent today, which had. You'll see.
Yeah, so I'll make those public, and and so we'll hone in on a couple of specific points, and we'll go through these different things that just seem intractable, and let's see if we find some solution for one side or the other. I mean, a resolution of some kind, because it really shouldn't be. It really shouldn't be a hostile, evil, horrible conversation to have about what is the truth and what does the evidence really point to. And that's all I want. And nobody should say I want anything else. That's what I want.
I'm surprised that one of these, Steve Mould or somebody like that, hasn't looked at it. But I suppose it's too big, right? You'd be going up against everyone. Because if you remember, there was a thing, I don't know if you saw it the other day, between Verisatium and somebody about some machine, like wind machine or something, and they got very into this whole debate.
Oh yeah, no, I did a couple of videos on it. Actually, I have the correct answer. so I actually have the best explanation. And I also did it with the chain fountain. I also did that one better than they did it. Okay, so my physics works even better. Momentum physics does work.
The chain fountain's really pretty interesting, right? That was I like the chain fountain was.
Yeah. So seriously though, I have there's a guy called Applied Science, does really nice technical videos.
Oh yeah, yeah. I know.
And he did one video where he talked about kinetic energy, showed the Newton cradle and all that stuff. And I said, well, can't you just go one step further, and actually show us an experiment that demonstrates the existence of this formula, please, please? But I got no response, But I would love to see him take, because he seems like an honest Joe who really digs deep. He doesn't just superficially do an experiment. He does it as deep as you can do it, and that's what it really needs to be done, deep, well,
deep
thorough,
and well,
thorough.
Yeah. Rather than like flicking little things out with
well, I'm just saying I've done this silly, I can shoot stuff with rubber bands, but don't we want a little better than that, like the high-speed camera and the whole smear, and we want to measure the heat, and we want to film it in infovision, and, come on, do it all right, not all sloppy.
It shouldn't be that hard, though.
That's the whole, right. How much does it cost? 58 cents, this isn't asking much.
That's what I mean. Exactly. It's not. This isn't rare. Rare stuff. I suspect it's too big. I suspect the problem is the minute someone does look at it, as I found, they start to look at it. I
just think that they have been. They're confident because it's so well established and so long a history. They just don't even think there's a possibility of reason to doubt. And I don't know. You know what I mean? I just don't think they have really thought about the dichotomy created by these two theories, where momentum, and they just been applying them by it's like wave particle, you know what I mean? They just choose, well, today I'll think of it as a particle, and tomorrow I'll think of it as wave. Depending on the experiment, I'll pick my choice. And they're settled for that, this compatibility notion, that somehow the two ideas are compatible when they're getting completely different numbers.
But eventually, one day, like the right answer is going to be there, right? Let's roll on 200 years. It can't be buried forever.
I agree with you. I don't know. I can't explain why, and I guess I became more and more certain. All you have to do is look at the history. The history is so bad, right? I mean, Leibniz being religiously, motivated, and then the fact that there was zero evidence and nobody was convinced, and and then they proved a theory they changed 100 years later. I mean, it's so bad that once you see that, you say, "Oh yeah, there's good reason."
Yeah, the adding the half.
There's good reason to do this over. Okay, this needs a do-over. And kinetic energy needs a huge do-over.
The fact they added the half. I mean, the trouble is, once it's in Maxwell, I hadn't realised that. Yeah, because Maxwell is like, that's like the Moses, the tablets or whatever, isn't it, Maxwell?
Well, yeah. So they hate to have to modify that. Oh, God
well, exactly.
forbid.
Imagine that, right?
Yeah. So
no one
yeah.
almost did that. All right. Nice speaking to you. Cheers, Gary.
Okay. Well, thanks. I really appreciate it, and we'll do it again and such.
Yeah.
All right.
Cheers. Bye.